So we have discussed about Bernoulli equation. Now I'll solve some numerical based on Bernoulli equation. Suppose we have the cylindrical vessel filled with water and has got orifice at the bottom. Suppose we have a cylindrical vessel which is filled with water and has got an orifice at the bottom. Suppose we have cylindrical vessel and it is filled with water, right? We have water inside and we have the orifice. We have the orifice at the bottom, right? So water is pouring out, coming out, and we have to find out the velocity of water coming out of the vessel. Velocity of the water coming out of the vessel. Suppose A is the area of cross section of the cylinder and the cross section area of the orifice is small a, with small a very small compared to the capital A. And suppose h is the height of water, right? H is the height of water. Now in this case we have to find out the velocity with which water is coming out, the velocity with which water comes out, right? This is the, suppose V is the velocity with which water comes out, and suppose V dash is the velocity with which water level falls down. Water level falls down with the velocity of V dash. Then from equation of continuity, I can say AV dash is AV. Now see, we can choose one position, strategic position as say P, and this can be another strategic position Q. So at point P, the static pressure is P plus, see, the static pressure is going out to be what? See, according to Bernoulli equation, P plus half rho V square plus rho G H equal to constant. Your P, the static pressure is, P is the static pressure. The static pressure, what do we mean by static pressure? The pressure when pressure of the liquid, assuming the liquid to be at rest. If suppose the liquid is at rest, what is the pressure over here? Pressure here is, this is in contact with the atmosphere. So it's P ATM plus half rho V dash square. This is kinetic energy per unit volume, and potential energy per unit volume is, if you want to find potential energy, you first take the reference. You take the reference for measuring height. This is reference, at here the potential is taken to be 0. So compared to this, at point P, your potential energy is rho GH, and that is constant. At point Q, again the pressure, this point Q is also in the contact with the atmosphere. Point Q is also in the contact with the atmosphere, so it is P ATM plus rho V square. This is the reference, this is 0. So this is constant. This is constant, 0. See here, this Q is in contact with atmosphere. So your static pressure is P ATM only. Static pressure is P ATM only. At Q, the static pressure will remain P ATM. What is the static pressure over here? Can you tell me? Can you tell me the static pressure at this point? The static pressure at this point is going to be the weight of liquid column, static pressure at this point is going to be P ATM plus the weight of liquid column per unit area. So pressure over here is weight of liquid column per unit area. So if I take a unit area, then the volume is going to be H. If I take unit area, the volume is H into 1 unit area. So H is the volume, H is the height into unit area will give you the volume, and rho H and G. This is the weight of the liquid per unit area. Weight of the liquid, that is P ATM plus rho GH. Whereas at Q, the static pressure is P ATM. Why? Because see, the weight of liquid column above this point Q will be under free fall. The weight of liquid column above the orifice will be under free fall. So this won't be there. So it's P ATM only. It's P ATM only. This weight, this won't be acting at Q, because Q at above Q, the liquid column will be under free fall. So it is P ATM only. The pressure is P ATM only, right? So it is P ATM. So that's why I'm writing static pressure at Q is P ATM, right? So they are equal. So I can write P ATM plus equals to P ATM plus rho V square plus 0. So this P ATM will go away, and V dash is AB by A. So rho and rho will cancel out. So rho will go away. So what we'll have is we have 2GH 1 by 2 V square, or you can say V square. So V is 2GH 1 minus A square by A square, and A is very small compared to A. So V is root 2GH. V is root 2GH, right? V is going to be root 2GH, and this is called velocity of efflux. We call it velocity of efflux, right? Or this is also called Torricelli theorem. This is also called Torricelli theorem. So the velocity of efflux is V is 2GH, right? If suppose you don't have the orifice here, I have the orifice here. Suppose I have my orifice over here. In that case, again, you have over here, let me find out, say I take point P remains same. Let's take point P at this point, and let's take Q at this point. Let's take point P at this point. This will hold us still, and water is coming out from this point. Okay, so at point P, again I have P ATM plus, if I take this as reference, P ATM plus half rho G. Suppose this is Say I call this as capital H and I call this as small h. So it's rho g capital H, right? Rho g capital H equals to constant, whereas at point Q, again Q is in contact with atmosphere, so at point Q you have P atm. If your static pressure is what? Pressure when the fluid is at rest. When fluid is at rest, the pressure is P atm plus 1/2 rho v square, and what is this height? The gravitational pressure point volume is rho g h minus h equal to constant. Rho g h minus h equal to constant. So in this case, if I apply Bernoulli equation over here, I'll be getting P atm and rho g capital H plus rho v square, right? So this will cancel out, and I'll write this as rho g h, and this will cancel out. So what will I get? I'll be getting 1/2 rho v square small a square by capital A square and rho g h. So rho will go away and your velocity becomes 2gh 1 minus this. Okay, so if A is very small compared to capital A, I'll get V equal to root 2gh. So what is important is the height of the orifice. See, what is important is the, you can say, depth of the orifice below the water surface. Depends on h. We're finding that the orifice, the water coming out of the orifice does not depend on this height. It depends on how much is the depth of this orifice, distance of the orifice from the surface of the water, from the surface of the water. Let's see this question. A wide cylindrical vessel 50 centimeter in height is filled with water. Rest on the table. We have a cylindrical vessel, something like this. We have a cylindrical vessel. It's filled with water. It's filled with water. We have the water over here. It's filled with water. And it rests on the table. Assuming the viscosity to be negligible, find at what height from the bottom of the vessel small holes should be perforated for the water height coming out to hit the surface at the maximum distance, L max. It just asks at what height from the bottom I must perforate. I must perforate a hole such that this L is maximum. It says about, we are asking about small height h, and suppose this is given to you, that is 50 centimeter, capital H, small h. So first of all, let's find the velocity. Let's take point P over here and point Q over here. At P, the static pressure is P atm, and say the velocity with which the water surface comes down is rho v dash square plus rho gh, that is constant, at Q. Again, Q is in contact with the atmosphere, so static pressure is P atm, dynamic pressure is kinetic point volume, that is half rho v square, and this is rho gh, gravitational pressure point volume. I have taken this as the reference, so that is also constant. All right, so if I equate them, so rho gh, so it's not V dash, it's V only, it's V. So, and we have an equation of continuity which says AV dash is AV, so V dash is AV by A. So if I take it on this side, 1 minus, and this is rho g h minus h, so rho will cancel out, and your velocity is 2g, and of course nothing is written, small hole, so I can assume the A to be very small compared to capital A. So this is 2g capital H minus small h, 2g capital H minus small h. This is the velocity. And what is L? L is, this is the velocity with which water comes out. This is the velocity with which water is coming out, right? And what's the time taken? Now it's free fall. Water is coming out, it's not inside, so H will be coming out like this as 2H by G. Time is 2H by G. So it's Vt so this is twice of, okay, so that's L, that's going to be our L. Okay, now to maximize L, so I need to maximize only this. I just maximize what is there inside, so I get d by dh, or this is h minus, so h is capital H by 2, h is capital H by 2, okay, small h is capital H upon 2, and what is L max? Small h is capital H by 2, so that's h. Small L max is capital H. Okay, so I hope you understand. I'll move to next question. See this question. A cylindrical vessel of height h and base area s is filled with water. A cylindrical vessel of height h and base area capital S is filled with water. An orifice of area small s, very small compared to s, is opened in vessel. Neglecting viscosity, determine how soon the water will pour out of the vessel. So I think it must be opened in the bottom, otherwise the height of the orifice would have been given. It is at the bottom. Let's assume that it's opened at the bottom. Because I want all the water to pour out. So all the water can pour out only when I have the orifice at the bottom, right? I must have orifice on the bottom, then only all the water will come out, right? Okay, this is the water. And we have an orifice over here. So water is coming out. Say it is H. Okay. Yeah. So H is the height of vessel, right? H is the height of vessel. So in that case, if suppose water comes out with velocity v, this velocity is going to be 2gh, Torricelli theorem, right? And suppose this velocity is v dash, and I can say sv dash is small sv, is small sv. Now your v dash is what? If the water comes out, height of the water will go down. So this must be minus dh by dt, because dh by dt will inherently be a negative number. dh by dt will be a negative number. dt is positive, always positive, and dh is negative because height is falling. And v dash, in order to make this v dash positive, v dash is positive, so dh by dt is negative, so I must put minus sign over here, right? Only then your dh by dt can be negative, v dash is positive, so I can write as minus dh by dt is small h 2gh, right? So this is going to be dh upon root h is small s by capital S 2g dt, right? At t equals 0, height is h, and we have to find time when height is 0, right? So the integral is going to be 2 root h s to 0 2g 0t. So this is going to become minus 2 root h minus s upon capital S 2gt. So the time taken comes to what? 2h by g. It will be, it will be 2h by g, alright? Time taken is capital S by small s under root 2h by g. This is the time taken by the water to come out. Time taken by the water to come out, alright? This is the time taken by the water to come out of the vessel. So this is the time taken, okay? I hope this is clear to you. This is an important question. So let's move to the next question. Say this question. You have a bent tube which is lowered into water stream as shown in figure. The velocity of the stream related to the tube is 2.5 meter per second. This V is given to you. This V is given to you. And the closed upper end of the tube is located at height h naught and has got a small orifice. To what height h will the water jet spurt? So you have two places where you are given the information. One is this point, let's call it A. Here you have the velocity of water, and this is one point where the velocity is 0, right? This is one point where the velocity is 0. Okay, so if I apply Bernoulli equation, then at A, what is the static pressure? What is the static pressure? P-ATM plus this. The static pressure is P-ATM plus, we don't know this height, so let's assume this to be H dash. This is going to be the static pressure. This is going to be the static pressure. And the kinetic energy per unit volume, that is dynamic pressure, is half rho v square. It's half rho v square plus the gravitational pressure per unit volume. What is gravitational pressure per unit volume? The gravitational pressure per unit volume is, for that I have to take a reference. Suppose I take this as reference. Suppose I take this as reference. Then the gravitational pressure per unit volume is minus rho g h dash. This is gravitational P per unit volume basically. This is gravitational potential energy per unit volume. And that's constant. That's constant. Okay? I hope you are getting this point. This is static pressure. If the water is at rest, the pressure over here is P-ATM plus rho g h dash. This is dynamic pressure. This is dynamic pressure. Half rho v square, that is kinetic energy per unit volume. This is gravitational pressure. This is reference dependent. If I take this as reference, it's lying down. A is below this reference, so I've taken minus. If I take this as reference, I'll take a 0. I'll change the reference and show it to you. Then at point, say B, your point B is in the atmosphere, so static pressure is P-ATM and dynamic pressure is 0, and with respect to this reference, the gravitational pressure is, this is constant, right? So if I equate this, rho g h dash, that is rho g h dash rho g h, all right? So this is going to cancel out. This is going to cancel out. You know V, you have to find H. So H is going to be what? V square by 2G minus H naught. V square by 2G minus H naught. I think it's correct. Yeah. V square by 2G minus H naught. Suppose if I take this as reference, then at point A you have P-ATM, this is the static pressure, and kinetic energy per unit volume is this, and this will become 0, that is equal to some constant, whereas over here at point B plus 0, this will be rho g h naught plus h plus this h dash also, that is constant, and you create them, you'll get the same thing. In fact, this will become 0 and this has come over here, rho g h dash. So ultimately they will cancel out, you'll get the same thing. If I take, say, this as reference, then what will happen? At point A, your equation will be again P-ATM plus rho g h dash, P-ATM plus rho g h dash plus half rho v square and minus of rho g h naught plus h dash equal to constant. And at point B you have P ATM plus 0 plus rho g h equal to constant. So only this term is reference dependent, right? So you can choose any reference of your choice, right? So this is how you can do this problem, right? Let's go to the next question. See this question. What work should be done in order to squeeze all water from a horizontally located cylinder during time t by means of a constant force? See, this is a constant force acting on the piston. The volume of water in the cylinder is V, capital V. Cross-section area of the orifice is smallest, the smallest being considerably less than the piston area. Okay. See, the work done is going to be, this is a constant force, so work done is going to be F into D. The constant force, the piston has to go till this point, so it's force into distance, but neither F is given nor D is given to you. Neither F is given nor D is given to you. Suppose the area of piston is A. So this is area of the piston is A. So I can write the volume is given to you. So D is V by A. V is given to you. Volume is given to you. So volume upon piston area is going to be D. So now we have to find F and A, or you can say we have to find F by A, right? Let's apply the Bernoulli equation over here. Suppose this is point A, say I used red pen, or say this is point P, this is point Q. So at point P, this is PT point P, your PATM static pressure is PATM plus F by A. See, when you apply force, static pressure becomes high over here, and your let's say the velocity with which piston is moving is V dash, and say we take this as the reference, so gravitational pressure is 0, and that is constant. At point Q is in the contact with atmospheres is PATM. Is constant. So what you find is your static pressure is getting converted to kinetic energy. This V is higher, this V is high, this V dash is low. This is the velocity with which you move the piston, and the water coming out is very high velocity. So what is happening is you generate a static pressure over here which got converted into dynamic pressure. When you push the piston, you generate the static pressure over here, and that static pressure gets converted into dynamic pressure. The pressure energy gets converted into K. The pressure energy gets converted into K. We have the equation of continuity also, according to which AV dash is, or AV dash is small sv. So this is going to be cancelled out, or this is rho v square 1 minus small s square by a square. So S is very, very small compared to area of the piston. So I can say this is approximately rho v square. So V is what? V is 2F by A rho, right? Okay, this is the velocity. I hope you're getting this, right? Now you have some information, more information. Time t is there. You need to empty the whole vessel in time t. First of all, you tell me how much amount of water is coming out per second. The water coming out per second is small s into V. Water coming out per second is small s into V. So water coming out in t second is going to be what? The whole volume, because in t, time t, we have to empty the whole vessel. So water coming out in time t second should be, time t should be the whole volume of the water. So this velocity is what? 2F by A rho into time t is volume. And from here we get 2F by A rho as V square upon S square T square, and F by A is rho V square upon 2S square T square. And if I put it over here, F by A, then it is rho V cube. So that should be the work done. That should be the work done. So this is how we apply Bernoulli equation. This is how we apply the Bernoulli equation. Okay.